shifted. It will be shifted towards the red. And that's shown over here. That's shown over here by the star going around in a circle, and that's the Earth over here, and it's emitting light towards us. And you'll see that as the star comes towards us, these black lines move towards the blue. So as it moves here, these black lines go this way. When it goes away, they move towards the red. So you can actually track the motion of an object just by looking at the locations of these lines in its spectrum. All you have to do is to find these lines. You know exactly what their wavelengths are in the lab, and then see if they're shifted. If they're shifted towards the red, the object is moving away from you. If it's shifted towards the blue, it's moving towards you. Very simple. And that's the idea. So the object's moving away from us, they show redshifted spectral lines, and the higher the shift, the higher is the velocity. And what is beautiful is that about 90 years ago, Edwin Hubble, in 1929, found that when he measured spectral lines of a large number of galaxies, he found that they were all moving away from us. So that's a plot from a much more recent work from Wendy Friedman and Bill Madore, which basically shows the velocity plotted versus distance. And you can see that all of these points are positive. All of these points have positive velocities. So each one over here is 10,000 kilometers per second, 2 is 20,000, 3 is 30,000. And you can see that as we go further from us, larger distances, the velocities are more. So galaxies are moving away from us, and the further the galaxy is from us, the faster it's moving. And this is called Hubble's law, that the velocity is proportional to the distance, with some proportionality constant, which is called the Hubble constant. Distant galaxies have higher redshifts. What is equally important is that we know that the speed of light is constant. We have experimental evidence for this. The speed of light is constant. This means that when we see a galaxy because light is coming towards us. And light takes a fixed amount of time to come to us from some object. So for example, the sun is 8 minutes away from us. Light takes 8 minutes to come from the sun to us. So what happens is that when you see a galaxy at a high redshift, you're seeing it as it was at an earlier time. Just as when you see the sun today, you're seeing it as it was 8 minutes ago, always. So high redshift means an earlier time. So therefore, if you want to track the evolution of the universe, you should find galaxies at higher and higher redshifts. The higher the redshift, the earlier the galaxy is when the light is emitted from the galaxy. That's the idea. You want to go ahead?
这边它成一张投影片是比较简单的物理概念，就是我们一般有个原子，那旁边的电子在那边绕，有不同的轨道，所以它的轨道是固定的，所以它每一个原子会放出它特有的波长，我们叫光谱线。我们现在在检查一些药物啊、食品，就是可以利用一些这些波长。那这些波长在实验室里面是固定的波长的，可是如果这个东西有离我们远去，会向着我们来有运动的话，那个波长就会改变，就好像警察会抓我们超速的时候也是一样，要利用这些杜普的效应，利用这个运动。那刚才的这张那张图啊，我常常认为它是大概上一个世纪最重要的科学发现之一了啊，就是它的纵轴呢，就是星系离我们远去的速度快慢，横轴呢是星系的距离，那居然有一个直线的关系。大家想象一下，等一下讲完演讲以后散场的时候，大家都离你远去，可是离你远的人啊，居然离你远去的速度比较快，这是一件很奇怪的事情。那后来对这个的解释就是它上面摆了一个 headline， 就是说只有一个状况会是这样的，就是如果宇宙中间每个角落都看到这个情形的话，就表示宇宙是在膨胀。所以他认为这今天演讲最重要的一个概念，就是要记得宇宙的现况是处于一个膨胀的状态。
So it said that the universe is expanding. What does this mean? So we said over here that all the galaxies are moving away from us. So this can happen, let's say a car is moving away from us. It has some velocity of its own. And so we think that these galaxies are moving away. But what the picture that we have for the expansion of the universe is not a physical velocity. It's not that each galaxy is moving physically away. What's happening is this. So these are two galaxies over here. What's happening is that it's not that these two are moving away. Space is being stretched. The whole universe is expanding. So the space between two galaxies is stretching outwards. That's the picture we have in the universe. It's not due to physical motion of the galaxies, it's a stretching of space. And as the universe expands, so if your length, which is so big, as the universe expands, its length becomes bigger. So now if I take a wavelength of light, which has some wavelength, as the space stretches, the wavelength also stretches. And so what happens is that all the wavelengths are redshifted. And that's the reason you see galaxies as moving away from you. All the wavelengths are redshifted away. And you have this the defining relation for redshift. The observed wavelength is some lambda rest multiplied by 1 plus z, which is basically all that you're seeing over here. All the redshifts are shifted towards the z. So that's the picture we have of the universe today. The universe is expanding. And now, suppose you go backwards in time. So now the universe is expanding today. But that means in the past it was smaller, and smaller, and smaller. So what happens as you go even further back in time? So the universe is getting bigger and bigger and bigger in the future. It's getting smaller and smaller in the past. So as you go further and further back in time, the universe is smaller, of course. So it's a much smaller universe in early times. But equally important, remember, if I take a balloon and let it expand, the gas in the balloon becomes colder. If I press something together, it becomes hotter. So at early times, at very early times, the universe was smaller, but equally important, was much hotter. And as you go to even earlier times, it gets hotter and hotter and hotter as it gets tinier and tinier. And so at extremely early times, the entire universe must have been really tiny and really hot. And the temperature is so high. So remember, as you heat something, you can break things up. So for example, when you heat water, for example, the bonds between hydrogen and oxygen, first the water molecules separate, become gas. If you heat them still further, the bonds between hydrogen and oxygen break up. If you go to even higher temperature, you can actually ionize the hydrogen atoms. So hydrogen is made up of protons and electrons, which are going around each other. When I heat this to a very high temperature, I can separate the protons and the electrons. If I go to an even higher temperature, the bonds within a proton will break up, and I can produce a mixture of quarks and gluons. So as I go to higher and higher and higher temperatures, I produce more and more smaller particles, subatomic particles, subnuclear particles in this case. And that's the picture that we have of the universe. At very early times, the universe consists of this huge soup, this huge mix of tiny subnuclear particles. And even before that, there was something called the Big Bang, just before that. And we don't know what the Big Bang actually is. What we know is that it's an explosion or expansion that pushes the universe outwards. We don't know our theories are not good enough right now to predict or to explain what happens exactly at the Big Bang. But our theories are good enough to tell you what happened very shortly after the Big Bang. So like about a millisecond or so after the Big Bang, we know what the physics is. At the Big Bang, we don't know. That's one of the active areas of research today. So something, we still don't know what, caused the universe to expand outwards and then to cool. And this universe now, right at the start, was full of these subatomic, subnuclear particles, a quark gluon plasma. So the picture we have in this Big Bang cosmology is that you started with an extremely simple universe, completely homogeneous, no galaxies, nothing, just a soup of particles, completely smooth, almost completely smooth, at very early times, milliseconds after Big Bang. And this same universe, expanding outwards, evolves into an extremely complex, inhomogeneous universe with billions and billions of huge galaxies. Each of them contains millions of stars, and of course, one of them contains us at very late times. So that's the picture we have in the Big Bang cosmology. You start with a very simple, tiny, hot universe, and you end, right now, you're in a universe which has all these huge galaxies. So that's a brief history of the universe as we think we know it. Over here, this point over here is the Big Bang. And we don't know, let me emphasize again, we don't understand the physics at the Big Bang. There's a reason for this. That's because in order to understand the physics of the Big Bang, we need to basically be able to understand the behavior of very large masses at very tiny distances. So basically, we need a theory of quantum gravity. We don't have that theory yet. People are working on it. So the hope is that we will answer that question at some point soon. But soon after that, in this period over here, the universe expands outwards, and for about a few minutes, about a minute, nothing much happens. It's just cooling. At some point, somewhere over here, so I'm plotting the evolution versus time over here. So this is about 13.7 billion years after the Big Bang. Somewhere over here, the first helium was formed. So right over here, you had in the beginning, you had this quark-gluon plasma. Then the universe expands, it cools, you form protons and neutrons. The protons and neutrons then merge together roughly about a minute or so after the Big Bang, and they form helium nuclei. And that's the prediction of the Big Bang model. You'll form helium, you'll form deuterium, which is heavy hydrogen, and you'll form lithium. Three species that are predicted to exist shortly after the Big Bang, a couple of minutes after the Big Bang. And then the universe expands outwards. At this point, there's definitely radiation, and there's definitely matter. And what's happening is that at this point in the universe, remember, it's very hot. So therefore, hydrogen cannot exist in the form of neutral atomic hydrogen. It exists in the form of the protons and the electrons are separate because the temperature is too high. So what happens is that you have this bath, you have this universe which is full of radiation, light. Remember, light is electromagnetic radiation. And you have a bunch of charged particles. You have protons and electrons. Electromagnetic radiation interacts with charged particles. So if I have electromagnetic radiation traveling like this, you will see an electron and it will immediately scatter off it. It can't keep going straight, it will bounce off it. And then it will bounce this way, you will see another electron, and it will bounce again, and it will keep bouncing all over the place. The effect is that electromagnetic radiation will not travel very far. It will just keep bouncing. It will tick around the place inside this region. And the universe keeps expanding. So the radiation is trapped inside by the electrons, and the universe keeps expanding. At some point, 400,000 years, 380,000 years after the Big Bang, the temperature drops. Because the temperature has dropped enough, now the temperature is low enough that the protons and electrons can merge together and form hydrogen atoms. So now you have a hydrogen atom, a whole bunch of hydrogen atoms, and this radiation is still there. But now the radiation is not going to see the hydrogen atoms, because remember, hydrogen atoms are made of protons and electrons. They're neutral. And so the electromagnetic radiation doesn't care about neutral particles. So at this point, the electromagnetic radiation can suddenly escape from this path. And it can travel in every direction, basically. So until this point, up to here, the electromagnetic radiation was trapped by the electrons. Here, because it cools sufficiently cold, hydrogen atoms are formed, and radiation is not trapped anymore. You can travel out. And the prediction of the Big Bang is that if you look in every direction, you will see this radiation at a temperature of a few degrees Kelvin. And that is predicted in about 1948. Because this thing is there, it's coming from all over the universe. The whole universe should be filled with this radiation. And so this is a prediction of the Big Bang, that you should see this radiation in every direction at a temperature of a few degrees Kelvin.
一个关键，我说我打断一下刚刚讲到说宇宙在一开始起点的时候呢，目前的科学是不知道起点到底发生什么事情 ，Big Bang 本身但是后来的物理就知道得很清楚而且现在形容说，原来温度极高的时候呢，东西都碎掉了，就好像你拿一个冰棒是冷冷的，可是你把冰棒一直加热，它就化成一堆线，再把它加热，它就变成蒸汽，再把它加热就 温度越高就越破坏成最原始的状态。那一开始的宇宙刚开始的时候很热，它就是原始的状态。那他刚刚讲到一个很关键的东西，就是在原始的状态的时候，这些电子啊、质子啊、带正电、负电的东西，让它绕在一起的时候，光是很容易被散来去、跑来跑去，不容易跑出来，不透明。就好像我们今天尘土飞扬的这个马路上的话，光就很不透明。可是如果这个尘土如果沉淀下去的话，我们就看得到光线。那这个比喻就是说，那个原来是游离的东西呢，光是不透明的，这是很关键的一件事情。因为等到差不多38万年、40万年以后，宇宙起源以后40万年，这时候温度降到电子跟质子结合成原子了，这时候就不是带电粒子了，这时候它对光线就不容易被吸收，这时候宇宙就变透明了。透明了以后，那时候发出来的辐射呢，随着冷却呢，所以刚才的预测就会看到宇宙微波背景辐射，因为那时候的辐射是各个地方都有，因为是当时宇宙整个地方当时发出来的，然后现在已经冷却到一个很冷的温度，它应该在微波的波段辐射最强，就等于就是这个是一个很关键，就是宇宙冷到一个地步会发出一个无所不在的辐射。
That's where we expect, in this epoch, about 400,000 years after the Big Bang, we expect to see this radiation in every direction.